Hi everyone. So the last couple of days we've been going through a general introduction of cosmological perturbation theory in order to see how the perturbations focusing on the gravitational potential and the matter density evolve. And yesterday we described both in a more formal way, trying to understand where things come from, and then with Sarah in the afternoon in a more intuitive way, what are the perturbations that we observe in the CMB power spectrum, and also the dependence that they have on the cosmological parameters. And as we saw, the CMB, thanks to all the features that it has in the power spectrum, is one of the main sources that we have for cosmology and to constrain the different cosmological models. One of the problems that the CMB has, though, is that, as we saw, the CMB is described by the state of the photons at the last scattering surface around redshift 1000, but we need to use a cosmological model first to describe the state of the photons at that moment, but also to evolve the perturbations of the CMB anisotropies and to infer low redshift quantities, such as, for example, the Hubble constant or the current matter densities today. This is why the CMB is a very model-dependent cosmological probe, and why it also needs low redshift cosmological probes like galaxy surveys or supernovae cosmology can be, in order to anchor that evolution of the universe at low redshift, and therefore be able to make the connection between today and the CMB in a much more controlled way. This is one of the problems regarding the Hubble constant tension, because the CMB predicts a very low value, very low with respect to what? It predicts a lower value of the Hubble constant, around 67, but direct measurements of the Hubble constant, as we will see today, predict at higher values. So one of the problems of talking about cosmic tensions is that these tensions are between very different cosmological probes, and that's why we are going through many of these observations. And today we're going to be covering a completely different part of cosmology. We're going to be covering low redshift cosmology and studying how we can measure distances and the expansion of the universe at low redshift in order to be understand the other side of the measurements for this cosmic tension. So the idea in order to measure this expansion history of the universe at low redshift is try to build a relationship between the redshift at which we are observing an object, like a galaxy, a supernovae, whatever it can be, with the expansion rate at that time to build the Hubble diagram. So at the end of the day, what we want to have is an H of C redshift relationship. And in order to do this, basically we need to have a good control of the redshift and relate it with the recession velocities and a good measurements of distances. Now, notice that the redshift, we are all the time assuming that is just due to the cosmological expansion, so it would be C Cosmo here, but it has some other contributions due to the peculiar velocities, delta C. The farther you go in redshift, usually this delta C is smaller, but you need to still take it into account and control it. But first of all, we are going to be discussing the ways in which we can measure distances in cosmology, and this is a very tricky subject because we are measuring very large distances in a universe that is expanding. And as we look further into the past in order to measure these distances, the expansion of the universe changes also with time, so we need to take that into account. As we've been using a couple of times already, we can describe the co-moving distance, which is the distance in a grid that already accounts for the expansion of the universe as, well, we can directly write it as the integral of the conformal time, but if we write it as function of redshift, that is going to be the main variable that we are going to use today to describe the evolution of the universe. Sorry, we are using natural units. it would be the integral of the inverse of the Hubble parameter. And we may also use quite sometimes the fact that the Hubble parameter can be described as H naught using the, the Friedman equations times the square root of, in lambda CDM, omega matter 1 plus c cube plus omega lambda plus some terms that in lambda CDM are not that important, or being a bit more general, we can write just H naught and some residual dependence on a function that we can call E of C. Okay. So as I was saying, measuring distances is not an easy thing in cosmology, and that's why known objects, such as can be standard rulers or standard siren or standard candles, and very recently also with the gravitational waves, standard sirens, are so useful. The idea is to have something that is standard, something that we know how it is and what it is, in order to compare it with how we observe it to be able to estimate the distance. So in order to have some very basic knowledge of these distances, that is what we are going to use today, let me first introduce the concept of a standard ruler, a standard candle, and these distances. So for the standard ruler, the idea is that we observe something here, and we have some object or known scale with a co-moving distance L that it's standing an angle alpha on the sky. This could be, for example, what we were discussing yesterday with Sarah and how we get the CMB, the H naught value from the CMB, and this could be, for example, the sun horizon. This is L is not co-moving, this is a physical distance. And by definition, the distance here that stands towards we are, it would be the angular diameter distance, which is the distance that closes basically and creates this triangle that we want to have. And since most of the cases this angle is going to be very small, we are going to have that alpha is L over dA. And if we want to have this in comoving units in order to compare it with the comoving distance, what we are going to have here is, in order to transfer this to comoving units, we have L over A at the moment in which the expansion rate of the universe for this, in which this object is. So here we would have L over A over chi, and that's why the angular diameter distance, it's 8 times the comoving distance, or the comoving distance over 1 plus c. Now, this is for a flat universe. For a universe that is curved, here you have a factor multiplying the comoving distance that depends on whether the universe is open or closed, but we are going to be considering all the time flat universe, so you can use directly this. Also, in most of the cases, since most of the descriptions that we are going to have about the known object or the standard rulers are going to be already in terms of the comoving distance, on in comoving units, we are going to be using the comoving angular diameter distance, that is moving the angular diameter distance to comoving units, and in a flat universe is directly chi. But we will be using the comoving angular diameter distance to be more general. And this is basically the idea behind measuring distances with the BAO, as we will see later today. BAO standing for baryon acoustic oscillations, and the sun horizon, and the sun horizon being the standard ruler. But before that, I'm going to describe how standard candles work and the luminosity distance. So in this one, the idea, rather than like building a definition of distance in terms of some known distance transferred to us on the sky, it's in terms of how we observe the flux of a source in an expanding universe. So if we have some source here that is emitting photons, the flux at a given distance here, common distance chi, is going to be the luminosity over 4 pi chi squared, where here the luminosity, I'm adding a prime, because is the luminosity of the photons that crosses this part, rather than the intrinsic luminosity of the object. And this is not the same, because since we know that the luminosity goes as the energy per unit time, first of all, we need to take into account that as the universe expands, these photons are redshifted. So the energy will be energy over 1 plus c, the energy of those photons. And also, we need to take into account that at this time, the photons are covering a different co-moving distance due to the expansion of the universe. So for a fixed interval in time, we care for the number of photons that go through that surface. And here we have an extra factor of 1 over 1 plus c due to the expansion of the universe between the source and this shell that, in this case, we will be here observing. So if we correct for these two factors here, we express this in terms of the intrinsic luminosity of the source, we have a factor of 1 plus c squared, and since the definition in a non-expanding universe would be the luminosity over 4 pi, the luminosity distance squared, or like a distance squared, we define the luminosity distance as the co-moving distance times 1 plus c. Again, as it was the case for the angular diameter distance, in a non-flat universe, here we will have an additional factor multiplying the co-moving distance, which would be this integral depending on whether the universe is closed or open, but something that holds no matter the curvature of the universe is the distance duality relation that stands that the luminosity distance is always 1 plus c squared times the angular diameter distance. And this is something that can be checked using supernovae and BAO measurements, for example, and still there hasn't been any empirical deviation found from this distance duality relation. Okay. So, as I was saying before, from the standard ruler in this case, we have that for the CMB, the angle corresponding to the sun horizon at recombination, which we can measure it from the first peak in the CMB power spectrum, is one of the best quantities measuring in cosmology. It is measured to very good precision, and this one is actually a model-independent quantity because we are just measuring the angle. We're not like here. It does not enter, is not entering any actual model of before or after recombination, and this is equal to the sun horizon at recombination over the Q-moving angular diameter distance. And in this case, these two are where the model assumptions are. Here, it would be the assumption of the model before recombination, and here, after. Because this is an integral from the beginning of the universe until recombination, and this is an integral from today to the recombination. And basically, from here, we can get a constraint or like an inference, because it's very model dependent, on H naught that is 67,27 plus minus 0.6 kilometers per second per megaparsec. The problem is that using standard candles in the local universe, the best measurement that we have comes from the cosmic distance ladder using CFITs and supernovae from the SUS collaboration. And if this is for Planck, assuming lambda CDM, the direct measurement from SUS is 73.04 plus minus 1.04 kilometers per second per megaparsec, which this is kind of like a 5 sigma tension between the two measurements. Now, I'm not going to get into definitions of tension, definitions or diagnosis of the inconsistency between two measurements. This is just taking the two Gaussian distribution for these measurements and computing just the number of standard deviations that they are away from each other. So we have been discussing the last couple of days how we measure H naught and how we can get H naught from Planck. We are going to discuss today how we get it from the local measurements using the distance ladder. Okay. So the local distance ladder, it's the only way to measure H naught in a completely empirical way. And with empirical way, I mean here, independent of the cosmological model that you assume, because it's basically built on the calibration of a standard ruler and at a small enough distances in such a way that the dependence on the co-moving distance on E of C is basically negligible. It's going to depend basically only on H naught. And the only assumptions that go into this kind of measurements is that gravity is described by general relativity, the universe is homogeneous and isotropic, and we can have either standard candles or standard rulers and so on. So the idea is, again, using some redshift that is low enough, such as the distance is the redshift times H naught, over H naught, and large enough, however, for the redshift to not be very affected by peculiar velocities. And this is because the peculiar velocities don't depend on the Hubble parameter. It will depend on the gravitational potential, and you want to remove those uncertainties from your measurements. So the kind of objects that we can use especially in standard candles that satisfy these two positions, are supernovae type 1a that are bright enough to be observed at very large distances, and we know that they should have, at the very least, a standardized luminosity. So the idea is, basically, we know what is the luminosity of the emission, and therefore we know what is, like we can infer very well what is the distance to it from the comparison between the apparent and the absolute magnitude. And basically, the luminosity, the absolute magnitude of the supernovae type 1a should be very uniform and standardized between different quantities, because basically what you have is a binary system in which you have a white dwarf and another object. The white dwarf keeps accreting mass from the binary companion until at some point, at around 1.44 solar masses, the carbon that is in the core of the supernovae starts to fuse, and that generates such an energy that cannot be contained by the gravitational potential of the star, and explodes in a supernovae that it's with a star that has always around the same same mass, and that's why we can have that the luminosity is standardized, and that's the idea of the known luminosity. So basically, from a supernovae observations, we can get a fit with the light curve, and we could get the maximum, like the peak of the luminosity of the supernovae, and also its color and its weight for the light curve. And that's basically the definition of the distance modeling. That is what we obtain from the standardization of the supernovae. And this one is given by the observed, the apparent magnitude of the supernovae. And where the apparent magnitude is defined as minus 2.5 the logarithm of the amplitude of what you observe. This is the amplitude of the light curve, the highest peak. And then for the standardization, there's a term that goes with the stretch of the light curve, the width of that light curve. There's also another dependent on the color. Of course, it depends on the absolute magnitude that of the supernovae. And then a couple of parameters that rely on some correction terms of selection biases and some residual correlation between the host galaxy of the supernovae and the supernovae luminosity. And this is basically the analysis that is done in supernovae cosmology analysis, such as, for example, the ones from SUS or Pantheon Plus, in order to obtain distances with respect to supernovae. The nuisance parameters here would be alpha and beta, which are global parameters. And these are also to be fit, but these depend on the specific properties, for example, on the host, and the selection bias on the properties of the supernovae. The problem here is that even if we think that the luminosity of this kind of supernovae type 1a, is uniform and follows this general relationship, such as we can standardize the luminosities, we don't know what is the absolute magnitude of the supernovae, and that's why we need some calibration for this luminosity. So, supernovae type 1a are a relative distance indicator or a standard candle. However, like if you take a bunch of light cores from like many supernovae and do this fit, you see that all the light cores after this standardization fall on top of each other. So like supernovae can be standardized. However, now the problem is do this calibration in order to get the absolute magnitude and compare it at the end of the day with the total luminosity distance in order to be able to build the Hubble diagram. The best way to do this kind of calibration and the best way that we can make an actual distance measurement without any dependence is using geometric measurements. But the problem is that those are limited to very close distances, and supernovae are rare enough events, such as like we don't have enough of them in our local volume, and we can't directly measure distance, geometric distances to supernovae, and that's why an intermediate step is needed. We need another rung in our distance ladder. So this is why these kinds of approaches usually use some geometric distance to calibrate some intermediate standard candle to get later supernova distances. So we're going to be describing kind of like this step, and this is basically why it's called the distance ladder, because you go one by one, going farther and farther on redshift. So the best way to do the geometric distances is through parallaxes, which is basically if this is the Earth, sorry, this is the Sun, this is the Earth and the translation movement. We have like the 2 points. We have some star here and some background of stars. This star, if it's close enough, we are going to observe them in different positions of the sky, depending on the position of the Earth. So basically, we can obtain its distance from this position, from this angle alpha between the position on the sky that we observed it at each point on the translation of the movement of the Earth. And basically, this angle at the end of the day is measured with respect to these background stars that are far enough that we are basically observing at fixed position, no matter what. So through this, we basically can calibrate the intermediate standard candle, and the most used or the most precise intermediate standard candles that we have right now are Cepheid stars and the tip of the red giant branch that I'm going to describe now. So the problem with those both measurements of distances, both Cepheids and the tip of the red giant branch, is that we can't use them to measure distances far enough to be sure that there is no contamination from relative velocities in our measurement of the redshift. And this is why you can't stop here, and you need to go to further distances using supernovae. And at further distances, supernovae are the only ones that are bright enough. So this would be basically either Cepheids or the tip of the red giant branch. I'm going to describe them now, but basically the idea here is to build the distance ladder would be something like this. So the relationship between the apparent and the absolute magnitude goes as 5 the logarithm of the distance in megaparsecs plus 25 in such a way that, let me do this, we have something like this. And you may have seen already this plot. It's not going to fit. So here we use geometric distances from parallaxes in order and plot 5 times the logarithm of the distance in megaparsec plus 25. This is here. And we compare it with the intermediate round here, let's say, for example, from CFITs. And we have some linear relationship, some data here, that allows us to calibrate this. Then we use here m minus m from CFITs, and we can extend this to further distances, comparing it with the difference between the apparent and the absolute magnitude from the supernovae. Again, here we have some measurements, and later we go here to distance moduli and obtain h naught here from the supernovae. Because basically by here we are at enough high distances to be sure that like the contamination from relative velocities is very small, and we have calibrated the luminosity of the supernovae with the local measurements of CFITs and parallaxes. Now, the main source of uncertainty here is that in order to do this calibration, you need to use first only the few supernovae that you can find in galaxies that you also have CFITs in order to be to do consistent calibration of them. Okay. So now let me discuss a bit, and if some of you have further opinions or doubts here, this may be a good time to to do them. What are the main properties of CFITs and the tip of the red giant branch as a calibrator? So we have CFITs and the tip of the red giant branch. As I was saying, this provides the two most precise measurement of h naught using the direct distance, the distance ladder. And it's important to have them into account because while this one gives you h naught of 73 plus minus 1 approximately, this one gives you 70 plus minus 2 from the Carnegie-Chicago Hubble program. And sure, these two are kind of consistent between them, but the big problem here is that this one is pretty consistent with the one with Planck. So there has been a lot of discussion between the groups using the CFITs or the tip of the red giant branch in the distance ladder to see whether there's actual attention or there's some problem measuring with CFITs. So CFITs are yellow giants, are like variable stars that empirically has been shown that there's a relationship between the age period and their luminosity that depends on the color of the star, and this is okay because we can measure the color well with photometry, but also on the metallicity of the star, and this is a problem because measuring the metallicities of the system is much harder and much harder to control. Now, another problem that the CFITs have is that they are usually found in a very high surface brightness regions, And basically, this gives you problems measuring them with crowding and blending. Basically, you are trying to measure the luminosity and the photometry of a single star in a field that is full with many other stars and like many other sources, so like you can have that problem. And you are also affected by dust extinction. That's since usually you are looking at regions of galaxies that are very close to the center of the galaxy, usually you are more affected by dust extinction there. On the contrary, the tip of the red giant branch basically uses the fact that uses the point of the core helium flash luminosity at the end of the red giant phase of evolution of stellar evolution for low mass stars. So in a magnitude color diagram, basically what we would have is this would be the main sequence for the stars in a globular cluster, the tune over to get to the giant branch, and at some point, a specific magnitude, here we will have what is called the tip of the red giant branch. And if you make observations of a globular cluster, this is a very strong cutoff here. And this would be the asymptotic branch and the horizontal branch. Now, the problem, this is like an absolute distance ladder. This is an absolute standard candle. It does not need to be standardized if we have perfect control of the stellar evolution codes and so on, and it also depends on the metallicity, which again is hard to constrain. The main problem with this is that there are less measurements with this, less calibrators, and so on. And even if it's found, and like the measurements are better done on the outskirts of the galaxies, such as you don't have problems with crowding, blending, and the dust extinction, usually the precision that you get from them is smaller because you have less calibrations at this step. So, as I was saying before, there has been a very big discussion between the two groups, discussing what is the best way to do this because they are not compatible, and there are several improvements that are ongoing for the two groups in order to this. That first of all would be increasing the sample of supernovae 1A here in the second rank, basically to improve the calibration of the supernovae at higher redshift. There's also an endeavor to improve the calibration of the two intermediate ranks of the distance ladder in order to have better control of them. It's very important also to have a homogeneous sample in both cases. You don't want your distance supernovae to be from a different kind of, like a different overall sample than the local supernova that you can calibrate. And also you want to observe all the parts here to build your distance ladder with similar telescopes in order to not include error of calibration in your telescope and in your measurements. And right now they are also doing observations in the infrared in order to improve all these measurements. Because, for example, one of the problems that they have is that the SUS group, when they have used their kind of observations and the observations with Hubble, which are homogeneous with their own, with the measurements that they use in general, they found a much higher value for each node. They have found a 72 plus minus 1 by plus minus 2 or something, which is in higher tension with Planck. So these are some of the problems that you have with the direct distance. Now, even if it seems that these measurements and the fact that using the tip of the red giant branch the tension is much smaller, doesn't gives less importance to the Hubble constant is not that much because there are many other measurements. The problem is that they have higher error bars that support and seem to be consistent with higher values of H0. They are all between the 73 and the 74 and so on, because you can use many other intermediate calibrators, and you can also use some direct measurements of distance, for example, geometric systems with the masers and so on. So I'm going to leave it here before the break. This is the more astrophysical part that I'm going to be discussing, because what we are going to discuss after the break is just not measuring H0 directly, but measuring the evolution of the Hubble parameter with redshift at low redshift in order to be constraining the expansion of the universe and anchor the expansion that we need to assume in order to evolve the predictions from Planck. So we can have a short break here now. Thank you. So yeah, we were discussing how to measure distances in the very local universe to obtain a cosmology-independent measurement of H0. But of course, we are also interested in measuring the expansion history of the universe at larger redshifts, basically to see, for example, if the dark energy behaves like a cosmological constant, or if there's some further components on the universe at the low redshift that we need to take into account. And basically what we are going to be covering now is these measurements of distances at low redshift that are dependent on cosmology. And of course, the first thing that you can do is, okay, we know that supernovae are a relative distance indicator, we know the distance moduli, and basically we can just, since supernovae are bright enough, we can just use cosmological supernovae that are at further distances. Usually we can measure even those that are at redshift around 2, measure the distance moduli from there, and we would get mu measurements, always with m, the absolute magnitude, as an unconstrained parameter, and since we can obtain m as function of mu, and the difference between the apparent and absolute magnitudes depends on the luminosity distance, we can get a constraint of H0. The problem is that this H0 is completely degenerate with the actually absolute magnitude of the supernovae. So at the end of the day, as I was saying before, supernovae gives you a relative distance indicator. If you constrain H of C as H0 E of C, we have enough supernovae to populate this Hubble diagram in redshift with many, many measurements. So it provides a very good measurement of E of C, which is the shape of the Hubble parameter. But we cannot constrain the normalization of the expansion rate of the universe. The only way to do it is use calibrations at low redshift, and therefore being completely determined by the local measurements of H0. So this would be what we will use for using the standard rulers, but the standard candles, but we can complement cosmological supernovae with baryon-acoustic oscillation measurements from galaxy surveys in order to measure very precisely the expansion history of the universe. So, regarding the baryon-acoustic oscillations, if you remember on the first day, we were describing the matter power spectrum, but only in terms of the cold dark matter and the radiation species, and we forgot about the effect of the baryons. It was something like this for the power spectrum, and I told you that there would be this effect here, which is actually the baryon-acoustic oscillations. Yesterday, we derived how the baryon-acoustic oscillations were on the moment of last scattering surface, because we were describing the evolution of the photon baryon plasma. And we saw that we had that forced harmonic oscillator, and we created that wave, that acoustic wave in the photon baryon plasma. Just as a recap, yesterday we saw this in Fourier space. We had that the modes that enter the horizon all the time would oscillate in time, but in configuration space, so in three-dimensional distances, what we would have, for example, is if you imagine as a function of distance some single over density of matter. Here we have cold dark matter plus baryons plus photons. As time passes, since we have the photons that want to leave this overdensity because they are not trapped by the, by the gravitational potential, we would have that cold dark matter stays here, but the photon plus baryons are leaving, this is supposed to be green, are leaving as an acoustic wave this overdensity, and this is basically because the baryons interact with the photons and don't let them just travel that much. And at some point after recombination, we are going to have the photons at that distance and, sorry, the baryons at that distance, and the photons would just like completely free stream and smooth. So if we look at the single overdensity from at a single overdensity, at the end of the day, our total matter is going to have a profile like this, something like that, where this is total matter, and this is the sun horizon at recombination, or if we are more precise, as Sarah was discussing yesterday, the sun horizon at radiation drag that happens just a bit later, and is the moment in which the baryons stop being tightly coupled with the photons. So this, after recombination, gets frozen in the matter distribution, but of course we don't have a single overdensity at any moment in the universe, so we have the superposition of all these pattern in the sky. So if we look, instead of like a single dimension, if we look at 2 dimensions, we will have the peak, the sphere, but then we will have here another, and so on. And that's why we need to use statistics in order to measure this peak of the baryon acoustic oscillation. A way to do this is either with the power spectrum, in which we are taking the variance in Fourier space of our overdensities, and for this we can use, for example, the galaxy distribution, and we would observe these oscillations that are the Fourier transform of this kind of peak, a broad peak. But if we work in configuration space in order to take this clustering, basically we can use the correlation function, which is the probability of finding a galaxy at a distance r from each other with respect to the uniform distribution. And if we plot r squared times the correlation function, of course, at very low distances, since we have this peak, this is very, very high, but then you have the broad peak at the BAO distance. And what BAO measurement from galaxy surveys use is basically use the fact that we can predict this sun horizon from the physics before recombination in order to use it as a distance, as a standard ruler, as a distance indicator, in order to measure distances. So now let me describe how we can do this. Okay. Now you have to think that we are looking at the distribution of galaxies in the sky that we measure as function of a given angle and like a given position on the sky n and redshift, and we want to compute the two-point statistic as function of distance, which would be the correlation function. So if we are observing here, we will have one galaxy here, separated by a distance r. But we don't measure this. As I was saying, we measure angles and distance. These two galaxies and redshift, these two galaxies are separated by an angle between them of theta. This is at redshift 1, this is at redshift 2, separated by a given delta c. And this distance, which we can break into transverse to the line of sight and parallel to the line of sight, are given by the transformation of the angular diameter, the moving angular diameter distance times the angle between the two lines of sight, and the interval in redshift over the expansion rate of the universe at that moment. Now, as you can imagine, in order to make this transformation, we need to assume some fiducial cosmology, because we need to assume some cosmological parameters in order to compute the distance to this point and the Hubble rate at this point. And the problem is that we don't know a priori which is the cosmology that describes, the cosmological model that describes the universe, or even for a given cosmological model, what are the correct cosmological parameters. So this, here, by doing this transformation, we can create an error. And as you can see, the error would affect differently the distance, the prediction of the distance that we make across the line of sight and parallel to the line of sight. We can correct this at linear level if we define a parameter that goes as the ratio between our predictions. In such a way that our true distance is the observed one times q. Okay, so at linear level we can correct that and basically look for the values of these two rescaling parameters. And there's like different effects here, because since this difference or potential difference between the fiducial cosmology assumed and the true cosmology affects differently each direction, so we add some anisotropy. So here we have three effects for potential anisotropy on our maps. You need to think that the distribution of galaxies a priori is isotropic, but we don't observe distances in real space. We observe the distribution of galaxies in redshift space, because here this C is C cosmo plus delta C from the peculiar velocities. So first of all, we have redshift space distortions that distort our map, and since this only affects along the line of sight, this is the first source of anisotropy. Now we have from the difference between the fiducial and the real cosmology, these distortions in the map, there's effect that is some isotropic dilation. And this is basically the fact that the volumes that we are going to infer between in our map may be different than the real ones, and this is basically goes as q perpendicular square, q parallel to the 1/3. And later we have the Alcock-Paczynski effect. I think it's written like this. And in this case, it's basically the anisotropic distortion that we create here, and this goes as the ratio of Q parallel and Q perpendicular. Okay. So for this, imagine that we have a measurement of the power spectrum. We can use these measurements to try to fit for this. The problem is that if we want to have a very agnostic and robust measurement, this prediction of this whole shape is very complicated. We need to include there a lot of uncertainties on the galaxy bias, which is the relationship between the matter over densities and the galaxy over densities. We need to account for all the effects of redshift space distortion. That is very complicated and so on. And here we only care about the error that we may have made here in order to recover the ratio between our assumed distance and the real one and our assumed fiducial Hubble parameter and the real one. So what we can do for this kind of measurements in order to only get this is marginalize over all of our uncertainties. And here there are different features, right? Like we have the overall shape of this power spectrum, and then we have the VAO feature on top of it. So what these kinds of analysis do is separate these two. So we have something that goes like this without the VAO, and then only the VAO pattern. And what the VAO analysis, the standard VAO analysis relied on is that, first of all, we assume a template for the power spectrum computed in the fiducial cosmology. So this is some fiducial power spectrum. We transform this fiducial power spectrum into P smooth without the VAO plus, or well, we can do 1 plus some VAO. This is what goes with the VAO. And in order to account for possible deviations in P smooth, we also add some polynomial that depends on K here in order to marginalize over. So if we do this and use the fact that our scales with respect to the observed ones, or the one that we reconstruct from our map in terms of angles and redshift, we can correct it linearly by the error introduced by the fiducial assumptions, would return us a measurement. And basically what we have to do is distort the template in order to recover the power spectrum. Now, I don't know if you noticed, but there are like a couple of, it's like a further uncertainty here and a subtlety here. We separate this. We are marginalizing over this. Marginalized over. And we want to focus on this. But the assumption of where these oscillations are, or if we work in configuration space, where this peak is in our measurement, depends also on a given fiducial cosmology. We have assumed some cosmology before recombination in order to assume here the position of the sun horizon, and we need to account for that uncertainty when we are distorting our template in order to fit the observations. So at the end of the day, the parameter that we fit for, instead of Q parallel and Q perpendicular, are alpha perpendicular that would go as, well, alpha perpendicular and parallel that go as Q perpendicular or parallel, and correcting by the position of the sun horizon at radiation drag between the real and the fiducial. So at the end of the day, what we fit for and can get from the bioanalysis is dm over rd over the fiducial prediction and HRD fiducial over the real one. In such a way that, like, since we have a good understanding of how the universe is, we expect these parameters to be one, but they're not going to be quite one, and they're going to be correlated, and the good thing is that they allow us to get information of both the expansion rate at a given redshift and the integral of the expansion rate towards that redshift. So they are also very complementary measurements. Now from here, we also get two effects. If we look, we are marginalizing over the redshift space distortions, but we still have these two effects. So if we think on the isotropic dilation, this gives us something that goes as alpha perpendicular square, alpha parallel, and all to the 1/3, which is proportional, if you use this, to 1 over h naught rd. Remember that the angular diameter distance is the integral of the inverse of the expansion rate, and we are leaving in the integral only the shape and getting h naught out. So from the isotropic dilation, we can get a constraint on the product of the zone horizon at times h naught. And if we go to the Alkov-Paczynski effect, what we get actually, it's, since this depends on alpha perpendicular over alpha parallel, this is something that goes as 1 over E of C. Goes as E of C over the integral of 1 of E of C. So at the end of the day, from the BAO analysis, what we get is a constraint on the shape of the expansion history and a constraint on the product of H naught and RD. So even if BAO are a standard ruler, since we don't know what is the ruler exactly, we have the same problem that we had with supernovae. We have a uncalibrated measurement to the distance ladder and to the Hubble rate. However, we can get a lot of intuition and a lot of constraining power for those two measurements. Okay. So here, let me plot the Hubble diagram, which goes as something like this. If I remember correctly, I'm not sure if there might be some factors of 1 plus c here. I always forget. But basically, we could have it like this. Supernovae give you a lot of measurements here, a lot of sampling up to redshift 2, approximately, but doesn't give you any constraint on the normalization. BAO, on the contrary, gives you a couple of measurements at a very specific redshift. We have, for redshifts below around 0.8, we have from galaxies. We have measurements at 1.5 from quasars, from quasar clustering. And then at redshift 2.4, we have the VAO measurements from the clustering of the Lyman alpha forest and its cross correlation with the quasar distribution. So basically what we get is in a supernovae plus VAO analysis, supernovae constrain the shape, and VAO constrain the normalization in terms of H0 times RD. Okay, so from here, we can either assume some specific cosmological model to compute H of C as the, for example, where E of C is the sum of omega matter times 1 plus C cubed plus 1 minus omega matter for the omega lambda and so on and so forth, and constrain those very well, or we can even be more agnostic. We can parameterize the expansion, the shape of the expansion history of the universe, either with, I don't know, splines, with some piecewise function, Gaussian processes, whatever method you prefer. And basically, at the end of the day, this is very constrained in terms of the errors that you have here. Got deviations that are less than 5% with respect to lambda CDM. And on the other hand, even with these super agnostic parametrizations, the constraints that you get in H0 times RD are smaller than 1%. And this one already gives us a lot of intuition of what we need or what we can have from a cosmological model in order to solve this. Even in the more agnostic way, giving the biggest freedom to our measurement, we predict something like lambda CDM, and this means that we can't have anything, any deviation from the cosmological constant, any dynamical dark energy or additional components at very low redshift that contribute enough to change H of C in such a way that we can accommodate a higher H0. So therefore, if there's something that deviates like lambda CDM, must be too small to solve this problem. And on the other hand, since we have H0 RD very constrained, we need something that changes the sun horizon at radiation drag. So this constraint, in general, goes as RDH, where H is H0 over 100 kilometers per second per megaparsec, is around 100 megaparsec over H. And what we have here is that if we use RD a prior on the sun horizon at radiation drag from lambda CDM prediction, which is around 147 megaparsec, we get, as expecting from Planck measurement, H0 around 0.67. If, in the contrary, we use H around 0.73 from SUS, what we get here is that RD is around 136 megaparsec. So basically, what we have here, and this is similar to the diagram that Sarah wrote yesterday on the discussion of how we measure the CMB from Planck, but this is without getting into Planck. This is using only supernovae and the VAO. If we want H0 to be around 73, we need some prediction that from lambda CDM, or like a deviation from lambda CDM, sorry, that reduces the sun horizon at radiation drag in order to be able to get a higher value of H. So even without taking into account the fact that we can constrain very well the shape of expansion at low redshift, we need some deviation at early times in order to get this consistency. Okay. Now, the good thing is that this measurement, we can either use some prediction using the best parameters from Planck, but we can also get it from a prior in omega b, the abundance of baryons from a standard Big Bang nucleosynthesis plus measurements of pristine gas. That basically would give the abundances of primordial elements in the universe, and assuming a model for Big Bang nucleosynthesis, we will be getting a priori in omega baryon in such a way that since from low redshift we can constrain omega matter, and we have omega baryon from this quantity, we can, for a given model, predict the sun horizon at radiation drag. So this measurement is very consistent with this 147. So even without any role of the CMB power spectrum, we have still this tension in H naught between the inferred value from the early universe and the local distances. And this is why, as we will discuss on Friday, there is the focus of the theoretical models beyond lambda CDM are on the physics before recombination. Okay. Is there any question related to how we measure distances with BAO and supernovae and the role that this has? Because I'm going to change to a different topic, but I think that we may have 5-10 minutes of like that we may finish before. So if we have any question with this? Okay, otherwise you can ask me later. So I'm going to talk about, finally, I think that it's going to take me only 5-10 minutes, about the other kind of measurements to get distances at a low redshift that you may have heard because they got a lot of attention in the last years, which is using strong lensing time delays. Okay, so basically, the idea here is that in a strong lens system, here we have some lens of deflector in such a way that for us, that we are observing here, if the source is here, we can see a couple of images, right? Because we will be observing this image, and therefore we will see this image here, image 1, and we could also see, for example, this, some image 2. And in this system, we are at a distance, at an angular diameter distance to the lens that goes as DD, that stands for deflector, a distance to the source that goes as, this is the distance between the deflector and the source, and then we have all distance from us to the source. And from Fermat, and the position of the real source on the sky is given by the angle beta, and this would be θ1 and θ2 for each of the positions. Okay. So in this system, we can use basically the geometry of the system and the Fermat's principle of the shortest time, the fact that this light is going to travel through geodesic, in order to see that the time that is going to take the light to travel from a position of a given image at a redshift is going to depend on some strong lensing time, in a time delay distance that I'm going to define later, given some Fermat potential, Fermat potential that goes as the difference between the angle, the position of the lens source and the lens image square over 2 minus the lensing potential for each image. And basically this lensing potential is the projected gravitational potential along the line of sight, given some kernels that we're going to discuss tomorrow when we discuss about weak lensing. And if we take the difference for this between the two images, they're going to reach with a time delay, one of the other, that goes as this time delay distance, and the difference on the Fermat potential for the two of them, where these two are 1 plus CD, and this ratio between the angular diameter distance to the deflector times the angular diameter distance to the source over the angular diameter distance between the source of the deflector in such a way that this goes as 1 over h naught. So strong lensing time delays could give you some value of 1 over h naught. There's some dependence on the shape of the expansion history, but a lot of that dependence is cancelled because you are using 3 distances that depends on this evolution of the expansion rate in the similar way. And all the focus here is basically left to the measurement of the time delays and the measurement of the gravitational potential. For the time delays, basically what you need is a very frequent coverage of the strong lensing system. Usually what is targeted are specific features in the luminosity of the quasars, and that's why you need a very good observation for those, because these features are like usually very small, and what you look is once you detect those in one of the multiple images, you keep observing in order to detect when it's going to reach from the second image. And you want to observe many of these cycles in order to get a measurement of the time delay from each image, which is good enough. But most of the theoretical uncertainty of this measurement is due to the actual measurement of the gravitational potential. Here, there's a problem with the actual lens. You need to have a model of the main deflector here, and usually this is done having additional observations. You can try to use spectroscopic observations of that lens in order to follow the orbits of the stars in order to derive stellar kinematics and have an inference of the mass. If you are lucky enough that you have Einstein rings on the image, that will give you a lot of information also on the lens, but that's not enough because you may have also some overdensities along the line of sight that may affect you and how you observe your image. And also, you may have what is called the mass sheet degeneracy, which is that the geometric portrait of the system is exactly the same, and you have the same observations, but this will provide is not changed if we add some constant surface mass to your surface density, to your lensing system. So basically, what that would provide you is that all the positions on the sky would be exactly the same, but you will be changing this and you will obtain the same time delay with a different time delay distance. So the mass sheet degeneracy, you can control it with some of these stellar kinematics and so on, but using only the lensing system would be totally degenerate with H0. Now, these measurements are very interesting and got that attention that I mentioned the other day because a few years ago, they were observing around 73, plus minus 2, if I remember correctly. So it was one of the best measurements that could basically corroborate the measurements from SUS. However, they decided to change a bit the way they will deal with the internal uncertainties of the lens modeling and so on, and now they have something like 73 plus minus 6. And there are different ways to deal with that. One of the things that they're doing, for example, is using lower redshift observations in order to have some prior on the properties of the lens that they may have. But these lenses are usually around redshift 1 or 1.5. So using galaxies at redshift around 0.2 in order to get that prior is a bit risky because we don't know if it's the same population of galaxies. So if they do that, they get, if I remember correctly, something like around 68 plus minus 3. And people will say, okay, then in that case, SUS is wrong. Because these measurements are supporting Planck, but we still don't know, and they are still getting better observations of the system and also looking for new systems. In principle, using measurements of James WST, the stellar kinematics can be resolved much better, and the model of the lens will improve significantly. Then these are the main ways to measure the expansion history of the universe at low redshift. I think that the main take-home message in this case is the importance of the sun horizon as radiation drag and the role that supernovae plus VAO, even in a totally model agnostic way, can give you constraints that are going to be very important in order to the model building and the designing of the model to solve the Hubble constant tension. And there are also other ways to measure distances that are uncalibrated. For example, there's something called the cosmic clocks that uses differential ages of galaxies in order to measure H of C, but the errors and the development of those measurements are still much less robust than, for example, supernovae and VAO. That would be the most robust measurements in general that we have for this. So if there's no question, I think that we can leave it here, even if we have still 10 minutes. And I just wanted to tell you that this is going to be all of the observables that cover the expansion history of the Hubble constant that we are going to discuss. Tomorrow we're going to discuss weak lensing measurements that affect the other tension that we have talked about it less, which is related with the clustering of matter at low redshift with respect to the prediction of Planck. And finally, the last day, we're going to make a discussion of the features that models must have in order to solve each tension and discuss some of the models that have been proposed in order to solve them. Thank you very much.